So, very good evening, everyone. It is my pleasure to warmly welcome our esteemed participants, our speakers of the day, our moderator of the day, and along with it, everyone who has joined voluntarily for this SADHANA Saptah 2026, our National Learning Week, which is envisioned as as a journey dedicated to nurturing the continuous learning with citizen centricity, advanced technologies, and also our Indian traditional knowledge systems in advancing towards the goal of Viksit Bharat. I extend a very warm and very special welcome to our distinguished speaker of the day, Professor Shantanu Chaudhury sir, and also our moderator of the day, Professor Kaushik Das sir. We are truly honored to have with you, sir. At the outset, it is my privilege to introduce our moderator for today's session, Professor Kaushik Das. So, Professor Kaushik Das sir is currently serving as a professor of practice at Gati Shakti Vishwavidyalaya, India's first central university dedicated to logistics and transportation, established by an act of parliament. In this role, he mentors BTech, MBA, and PhD students, as well as senior government officers and industry professionals in advanced areas, including supply chain management, infrastructure, network planning, aviation logistics, AI based forecasting, and advanced inventory control techniques. He also leads the university's innovation, entrepreneurship, and R&D initiatives in logistics and supply chain management. Currently, he is steering a industry-sponsored collaborative project on warehousing opportunities and challenges in India and is actively involved in the upgradation of Gati Shakti portal as well as the development of AI-based logistics simulation software in collaboration with BISAG N. He is also a nominated member of Task Force 4 of the Capacity Building Commission, focusing on sustainable financing, governance, and resource mobilization. Prior to his academic role, Professor Das had a distinguished 32 plus years of career in Indian Air Force as a commissioned officer, retiring in the rank of Air Commodore, logistics planning at Air Headquarters. He pioneered the establishment of Indian Air Force AI Center of Excellence under UDAN project and played a pivotal role in the development and upgrade of IAF's supply chain ERP system, IMMOLS. Professor Das is also an accomplished entrepreneur in the deep tech logistics space. He is the co-founder and CEO of Andro Rhythm Private Limited. Driven by a deep sense of patriotism and strong commitment to nation building, Professor Kaushik Das remains passionately motivated to apply his vast operational, technological, and strategic expertise towards strengthening India's logistics and supply chain ecosystem. His lifelong dedication reflects an innate desire to serve the nation by bridging cutting edge innovation with practical capability building in critical national infrastructure sectors. Thank you, sir, for your inspiring presence with us today. I now request Professor Kaushik Das sir to kindly take the session forward and introduce Professor Shantanu Chaudhury sir to the audience and initiate today's Karmayogi Talk. Over to you, sir.
Thank you, Rajatji. Namaste, everyone. Namaste, respective dignitaries, Professors Shantanu Chaudhury, fellow engineers, AI specialists, infrastructure stakeholders, and of course, all the team of Capacity Building Commission at a very important junction of SΑDHANA Saptah program. Yes, today we are talking about capacity building of civil engineers with particular emphasis on techniques of AI-enabled predictive maintenance. But I just wanted to take a moment before we start introducing our very distinguished panelists that we need to be mindful of the fact that India is building and maintaining the world's second largest road network, fourth largest railway system, one of the fastest growing metro networks, and perhaps an upbeat effort and a renewed effort on improving our coastal infrastructure. Perhaps we are talking about over 150,000 railway bridges, thousands of kilometers of highways, including the Himalayan highways. We're also talking about metro tunnels, which are boring beneath century-old buildings of Mumbai, Delhi, and other states. We're talking about signature sea links, which we are knowing about, Bandra, Worli, Mumbai transport links, and a relentless part of infrastructure push that the government is having. The question that comes in mind is it not true that perhaps a bridge girder is today inspected only visually after maybe a crack has come out? Is it true that the highways are only, we are taking action maybe perhaps when there are landslides that buries the road? Is it also a fact that metro tunneling settlement is only measured when cracks come in our houses? Or perhaps is it there that the coastal concrete structures are repaired, perhaps in certain cases where we have rust bleeding, which becomes visible? Now, as we move towards our infrastructure push, which is I can, in my personal capacity, I can see is exponential. The question is, do we need to move from a fix and find and fix mindset, a reactive approach, to something which is more predictive in nature? So when we talk about this, comes to the centrality of our talk, that is capacity building for civil engineers, with a special emphasis on predictive maintenance. And we're indeed very, very delighted to have amongst us Professor Santanu Chaudhury, an expert who has been in the forefront of integrating structural engineering and cutting edge data science. And if Rajatji, if you can just flash the slide, will help me. And let me introduce her and his accomplishments, which will give the audience a sort of idea as to how much we can engage him and get value of this discussion. Professor Santanu Chaudhury did his BTech in 1984 in electronics and electrical communication engineering and PhD in computer science engineering from IIT Kharagpur, India. Professor Santanu Chaudhury is at present the professor and dean in the School of Advanced Computing in Ashoka University. He is also the vice president, Indian National Academy of Engineering. Santanu Chaudhury, of course, sir did his BTech in 1984 in electronics and electrical communication engineering and PhD in computer science and engineering from IIT Kharagpur. Earlier, he retired as professor in the Department of Electrical Engineering, IIT Delhi, in January 2026. He had been Director IIT Jodhpur and Director CSIR, Central Electronics Research Institute. He was also the Dean Undergraduate Studies at IIT Delhi. He held a number of chair professor positions at IIT Delhi. Sir was awarded the INSA Medal for Young Scientists in 1993. He is a fellow of the Indian National Academy of Engineers, INAE, the National Academy of Sciences, NASI, and International Association of Patent Recognition, IAPR. He is also a recipient of the Distinguished Alumni Award of IIT Kharagpur. He has over 350 publications in reputed journals and conferences and 15 patents with technologies commercialized by the global industries. His areas of interest are computer vision, artificial intelligence, digital heritage, AR/VR, and multi-sensory media. Professor Chaudhury, sir, welcome to the fore.
Thank you.
It's indeed our singular privilege to actually have you on board. We would like to converse with you and like to know more of this particular very important paradigm shift that we are planning to have. And would like your initial thoughts, and then we will get into the discussions today, sir.
Thank you for giving me this opportunity to address fellow engineers and really the champions who are making our life continue in this, in face of various challenges and making things really progress in a positive direction. So I shall just share my slides, and with that, we shall just talk about the issue in more details. And in that context, how we can use AI. And I have kept my talk at a conceptually at a very simple level so that we can really appreciate the technology. And it's not really something which goes into deep into technology. So look at the public infrastructure today. If you see this is a created picture reflecting the Indian reality. All our urban infrastructures are actually, we have multi-layered flyovers, and we have the digital India as our target, and where we are looking at instrument because today's talk really reflects how digital India can transform our connectivity, our urban life, our production processes in industry. So public assets which we are using in the urban life today require maintenance. And what we are talking about are predictive maintenance. Why? If I can know when to predict to prevent a catastrophic failure, then we can make sure that this infrastructure and assets can continue long, and therefore we can have sustainable and safe services provided through our infrastructure. And this is very, very critical to also the economy of the country. The longer sustainability of these structures makes sure that our return of investment is higher. At the same time, since we are not going into construction so frequently, we also ensure sustainability of our environment, as well as the structures are maintained better, they are also less polluting. So these put together, I think it's extremely important to see that we are really having a process by which we are making sure that our life is much better managed with the process of predictive maintenance and management of our infrastructure. What are these infrastructures really? Physical infrastructures include transportation, which is I'm showing here. Then we have energy, we have industrial world, the water, drinking water systems, buildings, as well as telecommunication, because today telecommunication also is something very, very critical. Now, all of these, we want to do predictive maintenance. What does it mean? Therefore, predictive maintenance means that we anticipate failures before they actually occur. That means we are preventing any kind of catastrophe, any kind of abandonment of an asset before it's really to be abandoned. So therefore, we are doing timely interventions, and these interventions today are becoming directed through data-driven insights. Data is providing insight to us at what point of time we should. This is an example of, say, an Indian bridge which has been instrumented. And if you see, there are experimental work which is happening by taking data in real time as a train is passing the railway bridge, and how the railway bridge is behaving when a high-speed train passes through it. Because if it is stable, then obviously the vibrations would have a particular nature. If it is really not at the peak of its health, the vibration would show a different pattern. And these vibrations, these data, are being picked up through a variety of sensors. There can be accelerometric sensors, there can be fiber optic sensors, and these data is actually being analyzed through computers. And this is being shown that in real time, the data can be collected and looked at. And that was possibly the initiation of the structural health monitoring using instrumented interface. So here we can use a high sensitivity accelerometers, which use Hall effect, which is electromagnetic effect, to measure linear acceleration in three directions. Because these accelerations are actually indicative of the nature of vibrations that is getting induced. And based on that, we can predict abnormal character and the dynamics of the bridge changes. Dynamics of the bridge really tells us any abnormal changes which is happening or has crept in as the time has progressed. And hence, I need to do some repair work so that the life of the bridge is continued for longer. And this is exactly a typical example of an Indian railway system where bridges are close to about, many of the bridges are close to about 100 years old. Now, if you move forward, the question comes up is, as I have already stated, why predictive maintenance? Summarizing what I've stated is, it reduces unplanned downtime because we know that when to maintain and where possibly to stop the traffic on the bridge and do the maintenance work. It increases asset lifespan, optimizes maintenance schedules. We do not suddenly need to do a maintenance on the basis of an emergency call, but it can be pre-scheduled, pre-planned, and hence I can have an optimal utilization of my resources, including my manpower. And obviously, all of these increases operational efficiency. In fact, that's exactly the whole motivation of this Gati Shakti initiative as well as Karmayogi mission. And in fact, this is perfectly aligned in that sense.
Thank you, Professor Chaudhury. Just that gives us a fantastic idea of how we are moving forward. And I'm sure that when you are telling, could you just give us an idea on what are the foundational technologies, both in terms of maybe the algorithmic families and the sensing hardwares that definitely would be a part of this whole ecosystem that maybe a civil engineer must become comfortable with today, sir?
Yeah. So I'm just going into that. In fact, I'm just first trying to look at the different kinds of maintenance because the technology is linked with also modality of maintenance. So there are reactive maintenance that you fix after failure, which is having the traditional strategy for maintenance. And we also know about preventive maintenance. When you do schedule, we have a checkpoints in time and we actually do the maintenance at those checkpoints. But predictive maintenance is not scheduled, but condition-based, and hence it is more efficient and have low downtime risk. So therefore, what our focus is, that's why on predictive maintenance, increasing the efficiency of maintenance of our assets. Now, if you have to look into the technology, how the technologies really come into place. We put sensors. I've already shown you that there are sensors and I have instrumented a railway bridge. There are connecting wires. There are sensors on the railway bridge. And these sensors are also called our IoT device. That is called Internet of Things. So these sensors are actually making my bridge connected over the internet. Just like my computer is connected to the internet, my bridge or the asset is connected on the internet. So it's a thing on the internet. And because it is connected on the internet, I can also get real-time data from my assets. Then I need to do analysis of that data. The core technology which is used for analysis is machine learning algorithms, which can learn to detect failure patterns and predict the failure patterns. A predictive learning tells me that I can predict the failure patterns on the basis of the data that is coming continuously to me. And these machine learning requires huge volume of data because I need to gather the data over time. I need to gather the data over different kind of fault scenarios. So therefore, I need large volume of data, and large volume of data can be from different assets as well, on different kinds of assets. But what is important is that we need to have, therefore, mechanisms to handle large volume of data. Therefore, what we get into is big data analytics. And where will this big data be stored? Big data will be stored in the cloud. That means in the data stores, which are not located on the bridge, but far away from the bridge. That's why we are talking about cloud. And the cloud enables us to scalable data processing because I can have large compute power, large storage stored at really in the computer centers, and which can have the entire data over a larger period for a particular bridge. So try to look into it. It's very important and interesting to see that an asset generates huge volume of data. And actually, I learned the characteristics of that asset on the basis of the data gathered from that asset so that I know the typical pattern or possible pattern of failure in that asset. So this requires obviously instrumenting it, and instrumenting involves various sensors to be used. And the sensors on the asset really makes it an Internet of Things. So it involves therefore data collection, data processing, cleaning, pattern recognition, what we call AI ML models, predictive, then that AI ML models generates predictive alerts, and then the maintenance actions come in. So what kind of sensors we use? There's a variety of sensors if you look into it. And I've just given a few examples of them, and very common examples. Say vibration sensors, accelerometers. I've already given an example of accelerometers, how they are put on the bridge and the data is being corrected. Strain gauges, which are piezoelectric sensors. This measures stress, deformation of the materials. And these are particularly used to detect structural fatigue, because structures on the basis of the wear and tear, the fatigue develops. And if I can measure those fatigues and nature of the fatigue, then I can predict the failure point. And then based on the prediction of the failure point, the predicted time interval, I can intervene before so that this failure can be prevented. Acoustic sensors and emission sensors, these are detect microscopic structural properties, and these can be monitored using high frequency sound and often used for identifying structural flaws early enough so that they can be taken care of. Obviously, we have humidity and corrosion sensors because depending on the climate at different parts of the country, this humidity causes huge volume of corrosion, and that's to be tackled and handled. Then we have temperature sensors that can use temperature variations to monitor environmental conditions of materials. And when we have large buildings, we have the HVAC systems. So HVAC systems of large structures are also to be monitored to take care of various unforeseen scenarios. A very common sensors today we use, particularly for these kind of bridges and other structures, are fiber optic sensors. So we lay a fiber optic cable along the bridge with the sensors so that we can actually get optical data which measures the vibration on the object itself. And there are also standard pressure and tilt sensors. But these are just few sensors. And with that, I shall talk about later on how we use camera also. That is, computer vision is also becomes a very integral component for these kind of these structural property measurements so that we can create predictive models. So if you now move forward, what to do with this data? We say we use machine learning. What does machine learning really mean? Machine learning is nothing but using of the data. We have talked about two kinds of machine learning and deep learning. I think all of us are today exposed to these two terms. They have become almost a newspaper terms, and we encounter every day some report or other on these. And let's go back to some very basics. If we have learned in our childhood, we have learned with our teachers. Teachers have taught us various subjects, even starting from the basic alphabets, numeric abilities. These are all taught by teachers. So what we have gone through is supervised learning. So when machine also learns to detect faulty pattern in the data, they can be supervised. So an expert can actually say this data pattern is faulty, and machine learns that faulty data patterns. This is exactly what is your supervised learning. So if you see the data, this example here, what is interesting is, see this, there is a raw data. We process that data. Obviously, if the data is coming from accelerometers, there can be lots of noise. We may process it. Then subject it to a machine learning model. And this machine learning model is being trained. And this supervised training is there. This part is not connected. Okay. Supervised training is telling that this is a good pattern or a faulty pattern, which may require interventions soon. Okay. So if I say, therefore, these two binary class in which input pattern is divided, and I learn to classify the patterns in these two binary classes. So when I take, after the training is over, training is one phase. Once the training is over, what do? We take a data, but we don't have the label. We do the predictions. And when I find the predictions, in first we do a testing phase. When in the testing phase, when I do the predictions, I try to see the predictions whether they match what the human being have labeled or the experts have labeled the data pattern. This is basically testing phase of the system. Once the testing phase is done, I can rely on this data to give the signal that a faulty pattern is being shown. Now, the faulty pattern being shown is also to be verified by a human being. Therefore, it's not that we shall do completely, even today, I wouldn't advise, and technology has also not reached to that level, that I can completely eliminate a human being from this entire loop. So what happens is that a human being really checks whether it's working or not working, whether the prediction, and he makes use of his judgment to actually decide on the action on the basis of the prediction. So this is the machine learning loop, and this is a supervised machine learning loop. When there is unsupervised machine learning, then we don't know the level. And why, when we don't know the level, that when we don't know that, therefore we do not have a human expert to say that the data pattern which is coming, or this pattern is data is coming over time, the pattern that it's showing is faulty or not faulty, because it may be a too complex a system for a human expert to say it is faulty or non-faulty. Then what we do, we use unsupervised learning. When you use unsupervised learning, what do we use? Say, for example, the general data pattern, normally when we set things up, we see a common behavior. When there is an exception to that common behavior, that means there is a difference from what is expected. So there is an outlier. What we say is an outlier detector. But we do not use outlier as a label. We actually detect outlier on the basis of the property of the data. So we have, therefore, these machine learning algorithms designed appropriately so that it can say there's an outlier. For a supervised learning, machine learning model says that it belongs to a faulty class. Hence, you take an action. A human being decides on that what action to be taken, and also verifies the decision that the model is giving. Same thing is that when the model is flagging it's an outlier, it's not telling that it is faulty in that which category of fault it is, but it's not common. What is normally expected, it is not the expected pattern. Hence, that pattern is interpreted by an expert to take an evasive action. Therefore, this can classify faults, detect anomalies, optimize maintenance schedule, particularly reinforcement learning. I shall come to reinforcement learning that optimizes the maintenance schedule. So if you see, therefore, this is the detailed model. What is supervised learning? Supervised learning, I have labeled data. There is input-output pairs. I have labeled data. So the label for the input data, if I have an image, I know the label. So if I have images of apples and bananas, I know the labels that they're images of apples and these are images of banana. The learning algorithm learns to classify the images into either apple or to banana. And that gives me the trained model. Based on the trained model, when you give the new data, which are unseen inputs, I do the predictions. So this is exactly what I was talking about. The supervisor tells that these are really faulty data patterns, observations we are getting. These are labeled. Based on that, I learn the model. And using the model, I do the predictions. This is the most common type of this this predictive model that we create. When you go to unsupervised learning, this is what I said, anomaly detection. That is, there is an outlier which we are getting. So if you see, I have this collection of objects. If you see, these objects are all different. There are yellow circles, blue circles, red triangles, and then squares. These are different kinds of objects. But I do not know a priori what are the different types of objects and what are their colors or shapes. So this is completely unlabeled data. And an unsupervised learning algorithm discriminates abnormal from normal. Therefore, it discovers the clusters in the data. If you see that this system has separated out this whole collection of the data, which was not distinguished in their own way, but they were inherently they were different. They are being separated out into three different clusters by this algorithm. This is an example of unsupervised learning algorithm. So therefore, supervised, unsupervised learning is there, and these models are used. The standard models are used, therefore, for these purposes. Now,
So,
yeah, please.
sir, it actually prompts me to ask you because while I've been working a little bit on these areas in aviation, but definitely in the infrastructure side, we have seen some problems in when we deploy this model, especially for baseline modeling. We've seen issues of noisy data getting into the whole processing part. There are labeled failures available, or in case what I can anticipate when you have extremities of weather and environment conditions. So could you throw some light on the limitations of these models and what is the way ahead?
Yeah, I was about to come to that. Okay, so in fact, next slide exactly talks about the problems, limitations of machine learning. One of the big challenges with traditional machine learning process is feature extraction, because I cannot use a raw data. The problem happens is with change of variety of parameters, including temp, etc. So what we need to do some transformation of the data. That is called features. We would like to extract features from the data, which really represents the pattern of the data invariant to the impact of, say, environmental conditions. Modular environmental condition, those intrinsic characteristics remains invariant. So a machine learning requires discovery of those features and characteristics to do correct recognition, to have robust machine learning algorithm, which you are talking to. So therefore, this is something is very, very important why we go to deep learning. And I shall not get into details of deep learning, but deep learnings actually use capable of focus and right features by themselves, because I know I would like to discriminate between a faulty scenario and a correct scenario. So if I know that label data before, that this is a correct data and this is a faulty data, based on those data levels, I shall create the objective of the learning to learn to separate the data. In order to learn the separate data, I can learn the features which really highlight the difference between two classes of data. And that difference is learned in terms of distinguishing the classes that I've given. So if I have the deep learning models actually doesn't use a raw data, but it actually extracts the features which discriminates the classes which I would like to detect. So for example, given the data, I want to detect between faulty class and the correct class. When I have to take an action to repair, so I would like to maximize the difference between the class by extraction of the features and not by not using the raw data. So that's where you use a deep learning. This is one of the ways these failure problems are today being handled, because we're using much more sophisticated machine learning algorithm, which is deep learning. So deep learning is more to mimic our brain. That was the whole idea. But so if you see, this is a kind of an architecture that we use today. There are a number of layers. This is my input and this is my output. So this output, I know what kind of output it is. So when I give the input, I actually transform the data. Simple transformation is multiplying the data elements by the weights associated with these links. And then I sum it up, and that goes to the hidden unit. And the hidden unit again does similar things. So there are multiple such layers through which the data is getting transformed. And then it is indicating at the top layer, which is failure or non-failure. And we know what is a pattern, whether it would indicate a failure or not. So that is my level pattern. While learning, I know for a given data pattern, which output should light up, which output unit should really light up. So if that unit is not being lighted up, I know there is an error. So I propagate the error back from the output layer back to this layer. So this propagating the weight means what? The error means what? I adjust this connectivity weights. As I adjust this connectivity weights, I know under what condition the outer node to be lighted up correctly, because I know that given the pattern, which pattern should light up which node. So this is completely on the basis of supervised learning. And supervised learning, therefore, really takes care of feature extraction to make the learning system more robust. But fundamentally, one point you should note is that what are we doing is that we are learning to discriminate data based on their intrinsic or natural distribution. And that natural distribution is coming from the sensors that you're using. So therefore, if you change the set of sensors, then obviously the network which you have learned is no longer valid. Also, the behavior of a structure is based on the nature of the structure, based on the foundation of the structure, is built based on the art. So if you learn data for a particular installation or a particular bridge, you cannot use that model for another bridge straight away, because that bridge is built using a different structure. There is a different kind of a soil characteristics. So therefore, it has to be retrained, because the distribution of the data, which is linked with different fault stages or failure stages, are different from that of another bridge. So therefore, one bridge to another bridge, we need to be very careful in terms of building the models. We cannot blindly use one model for one infra to another infra. And if we try to do that, there is a failure. So this is something as a practitioner, we have to keep in mind that how we carefully adopt these models or retrain the models as it's required. So now, therefore, if we have learned these techniques, we come to what is called forecasting. Because exactly, if I summarize what I've talked about, I'm talking about the forecasting problem. Forecasting is predicting the feature values of the series using current information set. Current information set consists of current and past values of the series and other exogenous series, which are coming from the data. That means, say, for example, I'm taking data every 5 minutes interval. So I can take data over 2 hours with 5 minutes intervals together as a cumulative data set with respect to which I predict whether the health of my bridge is good or the health is not so good and some action is to be taken. And this is actually learned through supervised learning. I've explained supervised learning, where I have the label good, not so good, but failure prone. And this also is something which is interesting, is that I can learn in terms of using the label, I can learn also the forecasting interval. That means, do we need immediate action, or do we need a kind of a intermediate period action, or do we need after a long time an action? So therefore, if I have this kind of quantized time period, I can learn to predict over these quantized time periods and accordingly can plan our maintenance schedule and maintenance actions. So this is your line time series data. If you see that I have the historical data that I learn, and this is my neural network based, that model, that deep learning model that I've shown. So it learns and it predicts, forecasts the values. That is a prediction value. And therefore, these value, if you see, when it is very nice, given this value, I can predict this value, which is be very similar to this. Okay. But if there are some chaotic patterns in other places, it will indicate that where there is an error. Okay. So therefore, if you see that this, what is interesting is it is showing over time period. So I have done from time 1 instance to time 100, and then I've started predicting from 101 to 120. Based on the kind of inputs I get, there can be an expectation of the error coming at different time intervals. And based on these kind of a nature of predictions that is happening, this interpretation would also direct me to take actions. As far as this model is concerned, the action part is what is to be decided by a human being. So human is in the loop in this kind of a system. which also prevents kind of a wrong decision making or actually making sure that we take right action at the right point in time. But here, if you see that human being is being aided by a future prediction, so he's not just doing a preventive maintenance. Therefore, he can do the maintenance at the right point in time, and hence the maintenance becomes optimal. So therefore, if you see the whole picture is this, I have a sensor data, I have a machine learning model, which is a predictive system, and you predict the future sensor value. That's exactly what you learn. You predict the future sensor value, and the future sensor value is interpreted by preventive maintenance logic, which can be it can be an automated logic, or it can be a human guided logic, and that logic tells us whether I need action, or I continue operation, or I should schedule a maintenance action, a maintenance alert with a certain time period. So therefore, this is a flow of data. Flow of data starts from the sensors. This is where the computing comes into play. And then I have schedule a maintenance strategy. Now, when I schedule a maintenance strategy, how effective the maintenance is, how regularly I may need to do the maintenance, that can be learned through reinforcement learning. How? Reinforcement learning doesn't tell me whether it is correct or wrong. What it gives me a reward or a punishment. It doesn't tell what is the correct output I should produce, but it gives me a reward. So that means if I schedule a maintenance and I see an improvement at a particular point, I get a positive reward. If I don't do it at a particular point, I may not get that much positive reward. Obviously, this reward tells me how to learn optimal maintenance. See, it is just scheduling the maintenance, but the maintenance, scheduling the maintenance is fine, but how much, what kind of maintenance you will do at what, that feedback is also very important. And I can learn that feedback, and based on that, I can optimize my maintenance process. There, actually, the reinforcement learning comes up. I have not gone into deep into that because it's slightly more complex logic which comes up into play. So this is your reinforcement learning cycle. So agent is a decision maker till this previous point. If you see that schedule, maintenance, alert, etc., it is a decision maker which is coming to play. Now, decision maker is an agent. He can be a human being and can be also a machine. So agent suggests an action. He takes an action. So once it takes an action that is on the structure, your sensors again give me your, it gives a statement and it gives a reward, whether it's a correct or wrong. Based on that learns and the policy gets updated. Policy update means what kind of action to be taken when your system is flagging some error, flagging some conditions. Say action part is what is being decided by the reinforcement learning cycle. The detection part is being detected by supervised learning cycle. So this is exactly the core technology that I've talked about. Okay. Now, these core technology can be looked at in a holistic fashion to create what is called structural health monitoring system. This is a foundational principle which is today used for management of any asset that we have. Any physical asset that we have, we should have associated with that SHM. SHM is not a new thing. SHM is being used for a long time. But today what is coming in is that AI-driven SHM. In fact, whatever I have talked about so far, the technologies, AI technologies, machine learning-based technologies, supervised learning, and reinforcement learning-based technologies, these are actually parts of structural health monitoring system. So if you see structural health monitoring, AI in structural health monitoring has lots of these components. Data acquisition and sensor networks, because this is exactly I said, how from the sensors you get the data. And then on the basis of that, I can get the structural reliability and risk assessment done the way I've talked about. And we have not talked about visual inspection. We have talked about sensors, but now I already stated that as a sensor, we can use camera. When you use camera, we get what is called visual inspection. Visual inspection can be done using a camera attached to a infra or the asset. Or even today, we are using drones to fly over the assets to get the visual data to assess to remotely monitor the quality of the asset and how it is behaving when something, say, a remote railway bridge. We can fly a drone while a train is passing through it and then visually observe the vibrations and then can assess the quality of its health right now. So based on those data, I can have AI-driven predictive maintenance, which I already talked about, the way which is part of it. And also we also can do anomaly detection and damage identification. So damage identification means we have to make really interventions and take actions which may be more extensive so that I can extend the lifetime or the operational efficiency of the asset that you're dealing with. So this is the universe that SHM, and every component of the SHM is actually where AI plays a role. The key enabling component is data acquisition, where the sensors are coming. And it's not a one sensor, but actually a network of sensors which are deployed. And that data is actually analyzed through data processing, where also signal processing plays a major role. Because if you say a variety of sensors, data is coming, it's coming over time. So there's a signals. The signal processing also becomes component. So signal processing is a stage which is precedes our machine learning. And today's modern technology with the deep learning, the signal processing is also directed signal processing, which is also being guided by the machine learning system. So this is a real life example that therefore, if you see a bridge, there are these strain gauges, which are measuring the different kind of torsion and other tensions which are getting built in the in the bridge. Strain gauges is there. There are also fiber optic sensors, which are also measuring the vibrations. Measuring the fatigue in the structures. They're also these are being collected through data acquisition system. They're going to the cloud. On the basis of the cloud, there is analytics and their structural health report, and that is being provided an actionable insights to the engineering team who are managing this resource. So this is the whole loop of today's health monitoring system, and AI actually sitting here to generate an appropriate structural report and advice for the actionable insights.
Sir,
Yes.
I just thought a question came in my mind. In fact, if you can just show the last slide, sir, I think it is visually depicting the whole thing very nicely. Now, here we see a lot of strain gauges, a lot of accelerometers, piezometers, and a lot of things which you spoke earlier also. So is there a case in point where we also need to see that there is no decay in the sort of sensors, because they will only generate the data that we talk about. And if that is not in appropriate shape and it's not recalibrated over a period of time, then it may actually result in a lot of incorrect analysis. So what in your thoughts, sir, should be a good health monitoring system, not only for the bridges and all, but also to monitor these sort of important sensors, which form perhaps the fundamental aspects, because there would be environmental and other related decays.
Central Data Processing and Analytics Unit, because this is not a monolithic, I have just given a simple neural network learning to give a simple picture. But when I talk about data acquisition unit and a central data processing and analytics unit, there also every sensor is monitored with reference to the past data, what kind of drift it's coming. Is that drift consistent with other sensors being used? Because there will be multiple number of such sensors over there. And therefore, that kind of drift, statistical analysis of the sensor characteristics for a large structure is very, very important to detect whether these isolated sensors are misbehaving or not. Because what we assume is that if we use this kind of multiple sensors, why are you using multiple sensors? Multiple sensors are picking up different kinds of data, but these sensors also, since they're sampling at multiple points, they're also redundant sampling. The redundant sampling also tells you or gives us a mechanism to detect that whether these sensors are working correctly or not. If the sensors are not correctly working, I need to actually come in and intervene. So if you see here, therefore, dashboard or alert system is not just a single level output. It actually does the analysis of the data and producing a report, which is very, very important to see that how the sensors are also behaving. The other very important point is I am repeating it, this whole model has to be asset specific, because asset to asset, the behavior can change. So with reference to asset, I need to learn what is a normal behavior and how it is to be handled. So the ML system has to sit as a coupled with the bridge. In fact, this also leads to, I shall come to later on, with the concept of what is called a digital twin. So actually, we need to have a digital replica of this asset, which is a digital twin of this asset. And with reference to digital twin, many of these problems which are coming up with reference to individual part of the structure, sensors on the assets, all can be analyzed, detected, and predicted. So this is not just simply gathering of the data and application of a predictive model.
Right, sir. So, would you
I hope
also throw some light on you talked about it? Yes, sir. Yes, sir. Definitely, sir. Would you throw some light on how you are also using computer vision for these sort of technologies to add on to whatever you've already said, sir?
Exactly. I shall just get into that. So if you see here, therefore, computer vision is a very important technique also for structural health monitoring. So there are thermal imaging, and CNNs is convolutional neural networks. In fact, I have already shown deep learning. In the deep learning, we actually are nothing but convolutional neural networks where each node performs nothing but convolution operation. I shall not get into those. Just consider them as a deep learning. It learns to detect certain patterns. So these networks learns to detect patterns in thermal imaging. And thermal imaging provides heat signatures. That is how the heat is getting generated, variety of conditions on the structure, and also the cracks. I can detect cracks in the image, and also the thermal image, that spectral characteristics also gives me the heat signatures. That's also an indicator of the stress of the structure. And I already talked about imaging with drones, and that can capture inspection imagery remotely. So if you see that this is a dam, this is a bridge, and I have data acquisition using both camera and drones, and I can therefore take that image. I do image processing, do a feature extraction, and based on the feature extraction is where actually our ML is coming in, and using that I can detect the anomalies, and these anomaly data gets into structural analysis and diagnostics. So therefore, if you see, this is a first layer of ML, and this is a second layer of ML, and that is actually giving rise to decision making and reporting. In fact, this is the block which is the second level of ML, the meta learning which is taking place at this point. This is really the workflow that we use with vision. So this is an example. So this is a bridge that is actually the direction of the vibration of the bridge. Okay, and there is weight in motion at one cross section, because it also why this is important. So I'm seeing that given the loading of the bridge, how much of the vibration or the bending of the bridge is happening. So bending of the bridge is being picked up by the camera. Also post bending, when the load is removed, the nature of vibration is also being picked up by the camera in terms of image, the video that's being recorded. But the way in motion at one cross section is actually giving you also the data, the mechanical data. So mechanical data and the visual data both together is being looked at and for assessment of the load distribution, and given the load distribution, how the bridge is really behaving. So that's exactly a way to really measure the health of a bridge. So exactly this is what we're talking about, that if the structural responses records images and trains a neural network to recognize abnormal patterns across visualizations. To generalize, we compile a diverse set of images containing anomalous data and train the network. And to generalize across different structures, producing structure agnostic anomaly detector. So this is a second level learning, but this actually requires that it learns a bigger distribution. But most common is this part, that is, which is a bridge specific or an asset specific model. So there can be asset specific model And there can be models which are meta assets that can be used across assets. But today, most of the reliable results come with asset-specific models. Now, today, all of us know LLMs, that all of us are using LLMs in various ways, and that's giving you fantastic performance, and every day there is a debates about it. So the question is, can we use these kind of large reasoning models for structural health monitoring? Yes, that's where the future is, and they actually really give much more robust systems. So we distinguish between what are called small models and large models. We have so far talked about primarily small models. Okay. So large models are advantageous, and the goal is to cover many cases or to build unified, large model-based intelligent platform for structural damage diagnosis and maintenance decision making. So this, if you go back and look into these patterns can be specific to specific problems, structural problems that is coming up in the breach. But there will be variety of problems, different kinds of problems at different sections of that structure. Now to diagnose each of these problems, if I use to ML, I need to learn so many different patterns using a single network. And that makes things difficult. And particularly also, if we want to use from one type of breach to another type of breach, obviously the diversity is much larger. And so it cannot be done by a single kind of a network that we talked about. That's why I stressed upon all through that we have a model which may be a particular asset specific. But when we want to go beyond that, we actually go for large models. And large models typically offer super generalization and broader applicability across various scenarios. And here the generative AI powers these large models, and which is in the language also.
Sir,
Yes. Sir.
if I may just want to pick your mind. Sir, yes, today everybody is talking about generative AI and large language models, and you have rightly pointed out to the fact that these will be available. But I just was going back to when you started the presentation to say that maybe the bridge data of a particular bridge may or may not be comparable to a similar bridge at some other place because of the intricacies of the data and the parameters and the environmental conditions. So when we are trying to deploy large model, is it a case in point to go for overgeneralization and maybe at the cost of accuracy? Because if it's to be used in an Indian-based scenario, the Indian ecosystem and environment certainly has to be there. And do you think there'll be a need of a lot of training and creating our own models over the period of time? Or is it that we can straight away use it? Your thoughts on this, sir?
We cannot straight away use it. See, none of these ML models can be used. That is, I cannot use a model developed in Japan straight away here because my ground conditions are different and my model has to be fine-tuned and trained for ground conditions of India. The big model advantage is that since it's a large parameter model, so for example, today when you use LLM which is using English can also use Hindi. Okay, you can use, therefore it can actually make use of multiple languages. Even you can in English even, you can talk about literature and also talk on physics using the same model. These actually, so we talk about these large models as multitask models. They have been trained to do multiple tasks. Okay. So if there is a commonality between the task, if it is one aspect is between multiple bridges over a region, and if they have learned or ingested the data of all such bridges, then it can work over multiple bridges. I'm not telling that there won't be failure cases. There may be failure cases. And whenever you target with a single bridge, your failure cases will be much less. So what we have is we can use today, what we are talking about, we use this kind of large structure, but not go to billion parameters, go to smaller parameters and have a multitask model for a particular asset. So it may look into maybe a crack in the structure. It may be a problem in the foundation. All of these featured in a different way. But I can have a small parameter, large reasoning model, which can, with the data, which can reason to figure out exactly what problem has happened and what action to be taken. So this is an advantage. So if you see large model-based SHMs, means actually what we are talking about is multitasking ML systems. Okay. And obviously if I give more and more data, it has a better ability to reason. So therefore, if you look into it, it's an example of talking that why the large model can work better. It can combine multiple types of data. Okay. So it is actually looking at the image damage ID. Okay. From image, it can take background environment, it can take structure, it can look at components, it can look at the apparent damage data, it can look at multi-scale, multi-type, multi-level structural damage data set. So it's a huge data set. And it can be used also multimodal data. It need not be just the vision data. I can combine vision data with the language-based labeling of the vision data. We also can use sensor data. So we use multimodal data, for multitasking model. So it becomes a general AI engine to do kind of a prediction for action generation. Okay. So this is essentially using your generative models. So that is a generative model. How this generative model really works? It's based on all these data inputs. By learning from multiple sites, I learn, and then I actually generate a possible match with the data that I have given. So therefore, it is not predicting the class, it's going beyond the class. It's trying to see that the pattern that we have given is this pattern matching with kind of a problematic scenario, or the pattern matching is a normal scenario. So it can generate over the data to do the match, and hence it's a generative model. So if you look into it in a very theoretical sense, what is discriminative model? That given a distribution, whether a data point belongs to that distribution. What is the power of generative model? Given a distribution, a generative model can generate a sample which can match the given data. So I can say, okay, I have not seen it, but since I'm generating the data from the same distribution and it's matching, it's definitely therefore maybe a good data. And if it is not matching, that means there is some problem, I should take an action. So therefore, a generative AI-based system can be more robust than our standard small models, discriminative models, deep learning models that we normally make use of. And if you see here, by matching the results, and say a particular crack has appeared, can we match the crack? Can we predict the nature of the crack on the basis of the input data? That I can do only with the generative model. That's the full power of the large language models. Now, what we're talking about, if we are doing all of these, we can create digital twin of these assets, which are nothing but virtual replica. And what is the advantage of virtual replica? Then I can have this predictive analytics engine. I can actually take an action and I can simulate the effect of an action. And hence I can do a real-time update and check what is happening. And then I can actually take the action with reference to that. So digital twin is completely a digital representation of an asset. So if I have a bridge, there are multiple joints and I have sensors at all the joints. So I have the structural representation in the digital space. So just like I do a structural calculations for actually design of a bridge. So I have that design and I have the different joints. I have the sensor data for each of the joints. Once I have that data, I can predict through the analytics engine how the structure would behave. So now you can bring in physics. Since you have a completely digital replica of the asset, it is not just basis of the pattern that you are making a decision, but you can bring in physics in the digital space. Using physics in the digital space, physics-based reasoning in the digital space, you can try to understand what the fault is and what kind of action that you can take to manage the fault, or whether you can predict from physics, you can predict, and hence you can take actions based on the physics of the problem to ensure the longer lifetime of the asset. So predictive maintenance forecasts what and when the failure occurs. By using this digital twin, you can do prescriptive maintenance that recommends what actions to be taken and how. Because since you have the physics, you can also simulate the effect of an action. And you can take an action. So it's a prescriptive maintenance. Earlier, what was happening? I was suggesting that maintenance action has to be taken. An engineer is taking an action based on his understanding. And that action, I was talking about reinforcement learning in terms of scheduling of this action. Here now what we're talking about is that I can actually, using generative AI, and I can actually predict what kind of maintenance action is required. Okay. And that I recommend, and these actions to take and how it can be taken. So if you see this, there's a prescriptive maintenance flow for public infrastructure. And this is really where we are moving and we should move. And that can make the whole management of public infrastructure much more efficient, much more critical, and also the return of investment would be much more. Because if you see, this is my data collection and monitoring system, and this is my IoT platform. I started with the cloud. The data is now going to the cloud. It can go from water supply system. It can go for transportation network. It can go from bridges. And I also have the historical records and external data. It is not just the sensor data we are getting from there, from the past data we've taken. And that is being fed into analytics and AI engine. This analytics and AI engine is actually doing a machine learning models, and using machine learning models, I already have a digital twin. So I'm doing a simulation on the digital twin to do a failure prediction. That is from the machine learning model predictions, and based on the physics also, I'm checking whether really I'm doing a correct decision. If I know the failure prediction and I have done through the physical model, I can do prescriptive recommendations that what kind of action I need to take, what kind of repair, and when I should schedule that, and what are the water pressure, deploy road crew. So these prescriptive recommendations are also coming through generative AI, because those prescriptive scenarios I can simulate and see what will be effect of those on the digital twin, and hence I can have a very specific actions recommended on the ground, which is actually much more targeted and useful in terms of resource deployment to do the maintenance and preventive maintenance at the time. So it's not just a preventive maintenance, but how to do a preventive maintenance at a particular point of time on the basis of the data observed is what is prescriptive recommendation and prescriptive maintenance. So I then go into executive and feedback loop, the performance, and go that. And this is exactly where the historical data comes on. In the past, how much repair has been done? Is it that same spot where the fault is coming or not? So it gives me a comprehensive strategy for asset management. This is where now the whole world is moving. And we need to also move to make sure that our assets' longevity and sustainability ensured. So if we look at the comparative overview, predictive answers what and when, prescriptive answers how and what to do with differing AI sophistication and adoption strategies. So conclusions are, today, this whole technology is transforming maintenance from reactive to strategic. And this is something very, very critical. And this is the key to operational excellence. And in fact, we can invest huge amount of money to create fantastic resources. But it's very important these resources really deliver value. And if resources have to deliver value, I need to make sure I have operational excellence following a strategic maintenance plans. And that only drives sustainability and cost effectiveness. I think the whole mission that we are on today in the country, and the reason for which we are observing this week, this whole technology is one of the key elements to achieve that goal. Thank you. I'm happy to answer questions.
Thank you so much, sir. I think you took us through an amazing, fascinating journey of this whole very complex subject, but a very pertinent thing. Yes, sir. Let us take some questions if there are any in the audience.
I can stop sharing.
Yes, sir. So since today we are in the recording session, and this will be played during our SΑDHANA Saptah. So at that time, this session would be definitely played in front of our civil engineers, who would be from the PWDs and the urban local bodies and all such departments, which mainly work in the domain of civil infrastructure. So in the meantime, I have collected two questions for you, which pertain from the perspective of the civil engineers in the PWD departments. My question number one to you, sir, is that obviously when we are integrating such technologies, so this would have some added cost. Generally, from the governance side, if we see all the infrastructure projects, they have a pre-assigned budget. The budget is earmarked in advance that X amount of money is earmarked for this project. So we would like your insight on whenever such budgeting is done in future for any infrastructure project. What percentage of that amount do you think would be safe to earmark as an additional cost if one wants to integrate this technology in the cost itself? For an example, if we are making a budget of, let's say, 100 crores on any project, how much more, what percentage of it more should we keep so that if we can integrate this technology as well? This was question number one. I'll also keep question number two. That
So answer question number one, and then you come to the question.
all right,
number
sir.
two.
All right, sir. All right, sir.
So let me just look into this way that if you see the technologies that I've talked about, they have to be actually integrated when the asset is being created. I have shown an example to start with that we are doing a post-construction instrumentation of a building to do this kind of work. And that's what is happening today in majority of the cases across country, which are older assets. But today, when you are creating a new asset, it's very important to build in these things while construction. And in fact, it would cost about 10 to 15% of the overall budget outlay may increase right now. But if you look at amortize that cost in terms of the maintenance, subsequent maintenance, and the longevity of that asset, you'll find that cost increases actually amount to nothing. In fact, I myself have involved in some of these construction projects. Where we have installed these kind of sensors to get an assessment, which actually had helped us to detect some of the structural flaws and repair them before any major thing has happened. So this is the value, because subsequently, I would have to put money to rectify those things when something major would have occurred. So there would have been a cost. So what is important is that I can maintain my asset without incurring that cost, the larger maintenance cost, because I can predict them and take incremental small steps. So over the lifetime of the asset, this whole cost is amortized. And therefore, it really doesn't increase the cost of the investment.
Yes, totally agree with you on that, sir. And I'm really thankful to you for that perspective. That actually serves a lot of value to the engineers while designing the project itself. So, sir, with this, the second question would be, so as we are aware that in the case of India, there are a lot of projects today which are generally done either in PPP mode or in many times there are center and state governments, both are involved in some kind of project. So looking from the capacity building perspective, sir, what do you think from a managerial perspective, from an operational perspective, from the governance perspective? What do you think are the prerequisites? If I ask you 2 to 3 prerequisites that would be required in the manpower or in the skill sets or in the operational competitiveness of the human staff who are involved, or in the governance or in the systems, what would be those 2 3 prerequisites which will be there in order to integrate this kind of a predictive system into our civil projects?
I think one of the very important point is that today's civil engineering course also has to really change across the universities, because they are the basic manpower who are managing our assets. Today, data science is something which is very, very fundamental, because they have to understand data science and ML and also understand some of the sensors. These are basic engineering ideas. They will not be implementing it, but they got to have the appreciation of the technology to adopt this technology from the experts. The experts may come from also in a kind of a multidisciplinary background and multidisciplinary team. Civil engineers have to work with electronics engineers, because electronics engineers will talk about sensors and tell what sensors to be used, how it is to be used. And your data scientists and ML will develop the systems to make use of the sensor data to actually comment upon creating the systems which can do the prescriptive maintenance reality. But to appreciate what is happening, the engineers who are involved in management of the project when the project is being used. Say for example, if a CPWD or PWD engineers is managing a resort once it is installed, then he or she has to have an appreciation of these technologies which are based on the sensors and ML models. Without that, he or she cannot really deploy or really activate these preventive maintenance or prescriptive maintenance steps. So today it is very, very important and critical that in the civil engineering education also, this component is trained. And an engineer, when it's coming to the job, he or she should be also trained on this in a practical way, so that this capability really takes the whole infrastructure management to the next level.
Thank you so much, sir. I think you very, very lucidly explained the whole stuff. Allow me to close the session. We come to the more or less the end of the session. And a big thanks to Professor Santanu Chaudhury on behalf of the entire capacity building team and every participant, and who've been very keenly listening to you, because you started with the key technologies which are there in predictive maintenance. You touched upon the issues of supervised, unsupervised learning, its limitations. You took us from there to the deep learning aspects of it, talked a bit about forecasting, and then you talked about a holistic approach of doing it in a composite manner, introducing reinforcement learning. We also got a fantastic view of structured health monitoring systems for structural health monitoring systems, usage of computer vision, and then, of course, relevance of large language and AI models, and of course, what is it to be seen beyond in terms of prescriptive maintenance. So it's really been a fantastic journey. Thank you very much on behalf of the entire team. I would then call it today an end of today's Karmayogi talking session. Jai Hind.
Thank you. Jai Hind.
Thank you, sirs. Jai Hind.